Okay, time to start. I see everyone here but Jaron, is that correct? Yeah, no Jaron. Okay, today we're going to learn about electromagnetic waves, or EM waves for short. Now this picture gives all of the functional information we really kind of need for electromagnetic waves. So let me spend some time on this picture before we go into the theory of electromagnetic waves. So electromagnetic waves have as a fundamental relationship what we learned before: the electric field is equal to V cross B. Now, why is that important? It gives us two relationships. Now, one of them is the velocity, the magnetic field, and the electric field are all three mutually perpendicular. When you look at that equation, V doesn't have to be perpendicular to B, but it is. So for electromagnetic waves, the velocity is perpendicular to the magnetic field and to the electric field. And the electric field is perpendicular to the magnetic field. Everything's perpendicular. So in our picture down here, we have an electromagnetic wave that's going to your right. And so if the velocity is to your right, the electric and magnetic fields have to be perpendicular to your right, so they have to be in the up, down, or in and out directions. And they have to be mutually perpendicular. And so in that picture, the electric fields are vertical, going up and down. The magnetic fields are horizontal, coming out towards you, going back in. These are for you. Sweet. And the velocity is then going to your right. So the directions of the electric field, magnetic field, and velocity are important parts of understanding electromagnetic waves. Second, this relationship, because everything is perpendicular, also gives us the relationship that the magnitude of the electric field is equal to the velocity times the magnitude of the magnetic field. I put magnitude sign on 1. I didn't need to. As long as I take away the vector signs, that's true. So the magnitude of the electric field is equal to the magnitude of the velocity times the magnitude of the magnetic field. And in fact, at any moment in time, this is true. It's not just the peaks. So as the electric field gets stronger, the magnetic field gets stronger. As the electric field gets weaker, the magnetic field gets weaker. If the electric field is 0, what's the magnetic field going to have to be? 0, right. So the electric field and magnetic fields are alternating. I tried to show the electric and magnetic fields with my hands. So, electric field, magnetic field. They go like this is the way, whoops, I curved. They go like this, I did it again, as the wave moves. Darn it, this one was supposed to be going up and down. Okay, I don't do a very good job. Apparently I can't be a helicopter pilot. Should be going like that. I'm not going to try anymore. Apparently my brain doesn't have that ability today. Other things to note, we have sinusoidal waves. Now we studied waves before. And so we learned before how we can relate the velocity to that cosine terms. Anyone remember that from first semester? Nope. Okay. Well, how we can determine the velocity is if we stay on a single point of a wave, that is, we stay, let's say, the electric field is maximum. If the electric field is maximum, what is the argument for cosine? Cosine of what gives me plus 1? 0. Now, it could be 0 or 2 pi or 4 pi, etc. So let's go with 0 because that's the easiest one, since I get to choose. So I'm just going to make this argument 2 pi divided by lambda. Do you remember what lambda stood for? The wavelength. X minus omega t. Do you remember what omega was? Yeah, it's the angular frequency. It's the frequency in radians per second is equal to 0. Let's just solve that for x. Solve that for x. I will add omega t to both sides of the equation. So I have 2 pi over lambda x equals omega t. Next, I divide by everything that isn't x. And I end up with the equation that says x is equal to omega lambda over 2 pi t. Now, since I have something traveling, x is equal to velocity times time, so that stuff that time is multiplied must be the speed at which it's traveling. So this has to be traveling at omega lambda over 2 pi. Assuming I made no mistakes, which I don't think I did. So we can get the speed just from looking at the arguments of that cosine equation. This is a positive speed, so is it going to the left or to the right? With positive speed, it's going to the right. How did I get a positive speed? I got a positive speed because it had a minus sign in my arguments for cosine. If they were both plus signs, it would have been going left. If they were both minus signs, it would have been going right. But since one was a positive and one was a negative, or excuse me, if they were both minus signs, it would have been going left as well. With one positive, one negative, that makes it going right. Yeah, the right-hand rule I've already talked about. The speed of an electromagnetic wave in vacuum we call c. So this here it says speed of electromagnetic wave is c. That's only in vacuum. In any other material, the speed is slower. But in vacuum, we have the maximum speed for an electromagnetic wave that we call c. And c is defined to have a very specific number, 299792458 meters per second. And we'll see in just a few slides why that comes from James Clerk Maxwell's work. So a lot of information about electromagnetic waves just in this diagram. Yeah, question?
What's the little lines in 5 and 6 next to the pi and omega?
Say that again?
What's the little lines next to the pi and omega in 5 and 6? It's like
2 pi divided by omega.
Oh, okay, that's a divided by.
Okay.
Makes sense.
And 6, it's omega divided by 2 pi. Yes?
If it's V cross B, wouldn't E be the other direction?
Okay, so let's look at this. If I have this picture, if I put my, you're right, it has a minus sign. You are correct. I was wrong. Darn it. There's a minus sign there. I obviously didn't have it typed in here and went from memory and forgot the minus sign. Okay, so let's do what Chad did in his head. V is this direction. If B is coming out, my thumb points down. And the minus sign reverses it to make it go up. Thank you for correcting me before all is lost. Any other corrections? Okay, James Clerk Maxwell. One of the things I always like to point out is his father was born with the last name of Clerk. But he added on the name Maxwell after inheriting an estate from the Maxwell family. So it's not technically Maxwell's laws, it's Clerk Maxwell's laws. Clerk is not a middle name, it's the first half of his last name. It's the part that his father inherited from his parents. So James Clerk Maxwell sat down to try to figure out how electricity and magnetism work together. And what is it, 1950 or 1855? He figured out a set of equations, 20 differential equations that together would describe electricity and magnetism. And he published that in, what does it say, 61? And then another 12 years later, he had an epiphany and was able to bring it down to just 4 equations. And so now we have 4 differential equations, equations that we call Maxwell's laws, that describe everything in electricity and magnetism. And it'll be no surprise to you that we've been focusing on those equations, not all of the other ones. Because they're the only ones, we understand now, they're the only ones that are necessary to understand electricity and magnetism. So while they're still hard equations, as you'll see, they're much easier for us to work with. Now, James Clerk Maxwell, well, first the four equations, then the work by James Clerk Maxwell that's original to him. The four equations, the first one is Gauss's law. We've studied Gauss's law. Gauss's law was the recognition that electric field lines leave positive charge, go into negative charge, and so if I have a closed surface and I just count the number of electric field lines that go in and out, the net electric flux, the net amount of electric field going in or out, tells me how much charge is enclosed. So the first law relates to the charge enclosed to the flux. The second one, as far as you and I are concerned, is useless. In electromagnetism, it's not useless, but for you and me, it is. The second one is Gauss's law for magnetism. Magnets, unlike charge, always come in dipoles. You never have just a north magnetic charge. It's always a north with an equal south. So the net magnetic charge is always zero. And so Gauss's law for magnetism is the same as Gauss's law for electricity. It says that the total amount of magnetic flux coming out and going into a surface tells you how much magnetic charge is enclosed. But since the magnetic charge enclosed is always zero, it simply tells you the total magnetic flux for any surface is always zero, as long as it's a closed surface. So it's the same idea, it's just that the charge doesn't come in monopoles. You always have the enclosed charge as zero when it's magnetic charge. So Gauss's law for magnetism to you and me, meaningless. To deeper physics work, meaningful. The last two, Faraday's law. We've studied Faraday's law most recently, and Faraday's law said that a changing magnetic flux would create an electric voltage or an electric field. Now that's an important step there. A changing magnetic flux creates an electric field. So there's some kind of relationship between electric and magnetic fields. The fourth one is the Ampere-Maxwell law. We've studied Ampere's law. Okay, back to English. Ampere's law said that an electric current created a magnetic field. James Clerk Maxwell started looking at that relationship and he saw a fly in the ointment. He said, consider a capacitor. If I have a capacitor, and I know I made a big deal about this during my morning class yesterday, but not so much in lab. If I have a capacitor, I should have charge flowing to one side of the capacitor, charge flowing away from the other side of the capacitor, but what happens between the two faces of the capacitor? No charge flows. So that means there's current coming to one side of the capacitor, current leaving the other side, but no current in between. Now, Ampere's law just says you make a loop and you calculate the current that's enclosed, and it tells you what the circulation, the magnetic field parallel to the loop as you go around is going to be. And so what Clerk Maxwell said is, okay, let's take this loop right here. Just consider the left-hand loop. Don't worry about any of the other loops. If I take this left-hand loop, it would be typical to say, well, the area of that loop is right there. And so if I want to say how much current is going through that loop, I would say, well, it's the current going through that wire. Does that make sense? That's how we would all probably think about it. But he said, now that's not the way you have to do it. I could consider this like it's a balloon, and I blow up that balloon so that it goes like this and comes through here. And then I ask, how much current passed through the surface of that balloon? And what would the answer be?
Well, you have the current going in, but you don't have any leaving.
Well, no wire goes through that surface now.
So
So no current. Right? I deformed it, so now there's no current going through
But
it.
you were saying it was from, like a surface from the original, just expanding out.
It is. It's like we have, okay, blow with bubbles, right? You blow bubbles and it blows out like this.
But open. I thought you meant it closed.
Oh, yeah, it's closed there going between the plates.
Well, I thought you meant closed.
Oh, yeah, it's only closed on the blue line. So in that case, there's no current going through. And that is no violation of Ampere's law. But that would have said no magnetic field. And so we have a problem because we have a law that depending on how you apply it gives you two different answers. Only one can be right. And so Clerk Maxwell hypothesized that there must be some effective current when you have a charging capacitor. And so he called this effective current the displacement current. The displacement current, like many things in physics, turned out to be a bad name for it, but we still use it because it was what was originally named. And so he said, okay, I have a capacitor. The charge in the capacitor is CV, right? That was a basic rule for capacitor. Q is equal to CV. So that means that current is equal to the change in charge over change in time, which would be the change in CV over change in time. Now for a capacitor, the capacitance can be, you notice I'm just repeating what's down here. The capacitance has a physical value of, well, kappa epsilon 0 area over the separation. Using L here for separation so we don't get it confused with the D's in calculus. I put the kappa in here. Why is there no kappa in the equation shown? Because this picture has air where kappa is just 1. That's why. So if it wasn't air, you would have to have the kappa in there. So that's the capacitance. And then we know that if in a capacitor with parallel plates, the electric field is uniform, and V is equal to the electric field dotted to the length, which would just be EL. And so substituting those two, the value for the capacitance, the physical capacitance, and for the electric field, the voltage in terms of electric field, you end up with the derivative, well, epsilon 0. Nice. The change in EA over change in time. But EA, electric field times area, it turns out this really is rigorously the electric flux. So he said this displacement current is equal to epsilon 0 times the rate at which the electric flux is changing. And so that means that we need to really change Ampere's law. Ampere's law originally was that. And now he's saying, well, I enclosed actually needs to be changed to the I enclosed plus this I displacement. The I that's resulting from the charging of a capacitor or the building of an electric field and so there is the new form of Ampere's law as modified by Maxwell. So Maxwell added a second term, essentially, to Ampere's law. And that second term says a changing electric flux will induce a magnetic field. So now we had Faraday's law that says changing magnetic flux induces an electric field. And then Ampere's law says a changing electric flux induces a magnetic field. And when Clerk Maxwell looked at that, he said, wait a minute, changing electric field causes a magnetic field, changing magnetic field causes an electric field. We have a feedback system that can support a wave. And so Clerk Maxwell predicted there is going to be an electromagnetic wave because we have those two relationships, the relationship from Faraday's law and from Ampere's law. Yeah, go ahead.
I don't understand where his premise came from, because we spent all that time talking about symmetry and how important it was with a loop, and then he just draws a random balloon.
That was the symmetry for doing the calculation of the circulation. He's talking about how we calculate how much current is inside the loop. And so for the current inside the loop, you just add up whatever's inside the loop.
So you can draw any path of the loop? For finding the current, yes. But for the loop itself, we spent all that time in the symmetry because otherwise we can't really do the calculation. So here are the four laws that Maxwell put together. The two Gauss's laws, and then the Maxwell, here it's called Maxwell-Faraday equation because it has electric field, magnetic field. And then Ampere circuit law with Maxwell's addition. And those four laws describe everything electromagnetism, and they predict electromagnetic waves. So like next Tuesday in lab, or not in lab, but in class for the 252 people, we will go over how these four equations predict electromagnetic waves. Now, one thing to note is these are all calculus equations. There's really no two ways around it. Those of you in the algebra-based class have done this without calculus, but they're calculus equations, and you have a differential form or an integral form. So, for instance, the people in Physics 252 had to do problems using, well, a problem using this as well as problems using this, using both the integral and the differential form. We are not going to do, as a class, problems with these four equations. But it's important to understand them. If you're a nerd, it becomes super important. So people do things like this. They wear a shirt that says, God said. And they list the four Maxwell's equations. Notice I did two shirts because one shows the differential form, one shows the integral form. And there was light. Because light can exist because of those four equations. Now this actually plays into my understanding of creation. I believe that God set the laws of physics in place, and then after he set these laws of physics in place, then he put in the energy to create our universe. So he created the laws that govern it, hence in physics we're studying God's laws, and then he put in the energy so that we could have something besides just laws. That we could have something substantive. And so, yeah, that agrees with my theology. Yet, I am just not enough of a nerd to wear one of those shirts. First clicker question. How many equations are necessary to describe all of electromagnetism? Okay, 18 people said 4, and they are correct. 4 equations. Next question. How many of Maxwell's equations did James Clerk Maxwell create on his own? Okay, stopping now. 2, 0, 2, 2, 7, 5. No simple majority. We had the ASB election yesterday, or probably still running, right? And only one office has 2 people running for it. If there is not a majority for that office, you don't have a winner, right? You have a plurality, and you have to do something. You have to have a majority to have a winner, unless people just throw out all the rules of elections. The other people are running unopposed. If there are more no's than yeses, they should still lose. But that's not going to happen, I'm guessing. So we did have a slight plurality that said part of one. And those 7 people are correct. So now being specific, what did Maxwell do to get credit for part of one of the 4 equations? Okay, he added the displacement current part to Ampere's law. So if he only made part of one of these 4 equations, why in the world do we call these 4 equations Maxwell's equations? Yes, he did all the work in showing that just these 4. And as you can see, his first work, that was 18 years before the final one, had 20 equations. Nobody fixed it. Nobody said, no, you don't need this one, that one, until he came out with his second work that just said 4. So it was a good creative act on his part. It wasn't like obvious. He had to figure something out here. Okay, now, Maxwell, looking at those 2 equations, said this predicts a wave. And the waves are created if you have an accelerating charge. If you have a point charge at rest, it'll create an electric field but no magnetic field. If you have a point charge that's moving at a constant speed, it will create both electric and magnetic fields, but it won't create an electromagnetic wave. To create the wave, you have to have an accelerating charge. And, well, let's just go on to the next one. Here is how an electromagnetic wave can be created. You have, here it shows charge, positive and negative, that's accelerating up and down. And as it does this, it creates magnetic fields because of the motion of the charge, and electric fields because of charge separation, and creates those electromagnetic waves. Now notice the direction of the electromagnetic waves is minus V cross B. Notice the direction of the electromagnetic waves are propagating. What direction are they going? Mostly horizontally. There's a little up and down, but mostly horizontally, and none vertically. Electromagnetic waves are very directional. You might have a wireless adapter in your home. And the wireless adapters these days are getting really complicated. They have multiple antennae, and each one of those antennae is acting like one of these dipoles. And so they can make waves that go out in any direction except for the direction the antenna is pointing. And the electronics in those little Wi-Fi adapters actually adjust the phases. Remember, we talked yesterday about phase. Phase had to do with the time when you're at peak between those different antennae, so that you will have the waves of this antenna and this antenna and this antenna add up to give you constructive interference in that direction. And so it actually determines where your device is and adjusts the phases so that it's aiming its waves at you. And that way you have better coverage. And the complicated ones can actually aim at multiple positions. So you have waves going that way, waves going that way, and waves going that way. You need more antennae to be more specific in your directions like that. So there's a lot of interesting wave things going on just right there in your Wi-Fi adapters. If you're directly over the antenna, it's really not going to work well. So it bedoubles my wife. We have the antenna directly below our bed. It just doesn't work well here. Yeah, I know. What am I going to do? Well, there are reasons that it's there besides any preference. Here's a typical type of dipole antenna. Now, if you're interested in learning about radios, I know a number of you took the ham radio class, but they teach ham radio classes apparently all year round in the room across the hall in the evenings. What evenings is it?
I didn't think it was all year round there.
Oh, they start a new one as soon as they finish the old one.
Oh.
They may not go during the summer, but they seem to go all school year long.
I didn't think it was a union that they did it. I think that was just a special.
No, it's still going on now. But
Tuesdays at 6.
Tuesday to 6? Yeah, that seems right. You guys paid a lot of attention, did you?
just never went.
Just went and passed the test. Yeah, they told me I should just come take the test, but I didn't feel the need to. So if you want to understand the stuff carefully, they understand more about antenna theory there. Now, the things that are underlying, they kind of gloss over. Like their Ohm's law work is very simple. I think you agree, right? But you have an antenna here, and you just create a current that goes one direction and then the other. And so charge accelerates up, then accelerates down. And as it does so, it makes electromagnetic waves that are primarily going to have their velocities going out sideways from the antennae. Now, of course, you guys may not have rabbit ears in your televisions anymore, but when I was a child, we had the little rabbit ears in the back of our television. And you're always sitting there trying to figure out, now, what angle should I make them and how should I orient them to try to get the best signal? Well, those rabbit ears work pretty much exactly like you would expect. You have an electric field. An electric field is going to cause electrons to be accelerated. So if you have your antenna parallel to the electric field, you'll have the biggest acceleration of the charges and develop the biggest current in the antenna. And then that current antenna, you have a wire connected to it, and that's your signal that you're picking up. So if you change the angle so that it's not parallel to the electric field, you're going to get a weaker signal. And with your rabbit ears, it's actually, I believe, it's a ground plane and the antenna. So you want one to be perpendicular to the electric field and the other one parallel. But, you know, as kids, not just as kids, nobody knew. It was voodoo. How do we adjust these to try to get it best? Even if we knew where the signal was coming from, it's not perfectly easy. Because as the signal travels over the earth, it does some rotation things. The rabbit ears are designed to pick up the electric field part of the electromagnetic wave. You can also make an antenna to pick up the magnetic field part of the electromagnetic wave. To pick up the magnetic field, you make a loop, and as the magnetic flux through that loop increases and decreases, you will induce a current in the loop. And so if you have things like your stereo usually comes these days with a loop antenna. How many people have seen the antenna for a stereo that's a loop antenna? Well, that's surprisingly small. Anyway, those are designed to measure the magnetic field variations in the electromagnetic wave. And so you want those oriented so the magnetic fields are going to go into and out of the loop to get the strongest signal. So here's a picture just showing how a loop antenna works. Let's move on. We are not going to have any significant problems with antenna theory, but these are just basic things to keep in mind if you have a question relating to antenna that, you know, kind of very thin coverage questions that we have. If you have a rod, that's going to pick up the electric field, and you want to have it oriented parallel to the electric field. If you have a loop, that's going to pick up the magnetic field. So you want it oriented so the magnetic field goes into and out of your loop. A dipole antenna radiates in the directions that are perpendicular to the antenna. So if I have an antenna, my grandfather used to rent out a field to a radio station, and they had an antenna in the field. The antenna was a vertical antenna. So what direction was it trying to send its radio waves? Out horizontally, right? So that's why you have that vertical antenna. Doesn't radiate up this direction. And yeah, that's enough for that. Electromagnetic spectrum. One of the interesting things that Maxwell did is he calculated, which we'll see on another slide, what the speed of an electromagnetic wave was. And he found that speed of the electromagnetic wave was the same as the speed of light. And so he posited that because they have the same speed, they're the same thing. Is that logical? let us suppose that I run the same speed as somebody on a little dune buggy. Does that make me a dune buggy? No. That's generally a poor way of identifying that they're the same thing. But that was Clerk Maxwell's assertion. And Heinrich Hertz is actually the person who did experiments testing how light waves work compared to how electromagnetic waves work, and saw that they worked the same ways, and then concluded, yes, Clerk Maxwell was right. Light is an electromagnetic wave. So now we understand and readily accept that light is an electromagnetic wave. But Clerk Maxwell's original assertion was kind of ridiculous. Things like, we believe that the gravitational waves that were just discovered this past week also travel at the speed of light. But we do not posit that gravitational waves are electromagnetic waves. Right? But that's essentially what Clerk Maxwell did. Okay, so here we see a spectrum of frequencies. We separate out the different electromagnetic waves by frequency. Or we can separate it by wavelength. So you see on the top it says wavelength, on the bottom it says frequency. Either one will describe the wave. Why? Because frequency and wavelength, as we learned last semester, are related by the simple relationship frequency times wavelength is equal to speed. Now, if you're in vacuum, what's the symbol we use for speed? C. So I'm going to change this to C, but you have to understand that's then the frequency in vacuum times the wavelength in vacuum is equal to the speed of light in vacuum. So when you look at this spectrum, they're all electromagnetic waves, so they're all bound by the same rules. And we start on the left-hand side, and we have this right here, 60 hertz. 60 hertz electromagnetic waves. You might say, but we have wires, and we have the electrons that are moving slowly through the wires at speeds of centimeters per second for our electric signal. How is that an electromagnetic wave? Well, remember, when you flip on the light switch, it doesn't take minutes for the lights to turn on. They turn on instantly. And I explained it before by saying it's a chain reaction. But the real truth is that the wires that are doing this, we call them wave guides. They're guiding electromagnetic waves on the outside of the wires. And then those electromagnetic waves on the outside of the wires is what causes the drift velocity of the electrons within. And so the speed at which the signal goes from the light switch to the light is actually the speed of the electromagnetic wave in the insulation around the wires. You have a question?
Yeah, so are channels just ways of changing the frequency slightly?
Yes, different channels are just different frequencies. Now the channel system has been modified quite dramatically in the last 10 years. Right? The UHF frequencies were reassigned for digital, and the VHF. UHF is ultra high frequency, or a Weird Al Yankovic movie. VHF is very high frequency. And different frequencies are assigned different channel numbers. And surprisingly enough, it doesn't go 1, 2, 3, 4, 5. They kind of jump around. But yes, they're just describing different bands. Okay. And the actual definitions for those bands was changed when they changed to the high-def broadcasting standards. Okay, so the 60 hertz, that's an electromagnetic wave. We usually don't think about it as an electromagnetic wave because it's a very low frequency compared to other frequencies of electromagnetic waves. We go higher and we get to radio waves. Radio waves have frequencies in the ballpark of 10,000 to, what, a million? Not a million. 10,000 to 100 million hertz. On your AM dial, you're measuring in kilohertz, right? It goes from like 540 kilohertz up to 1,000 and some, I don't remember the top end, 1450 maybe, on the AM dial. So it's going from, if it's 540 kilohertz, that's 5.4 times 10 to the 5th hertz, up to 1.45 times 10 to the 6th. So your AM dial is somewhere in this ballpark. And then your FM dial goes from somewhere around 86-ish megahertz, so 8.6 times 10 to the 6
or 10 to the 7th, sorry, up to 100 and somewhere around 109, 108. So the FM dial is up here. So you're just using different frequencies. Now, there are reasons for different frequencies. The higher the frequency, the more data you have per second. Because you have more cycles per second, you can put more data in there. So if you want high quality sound reproduction, FM's probably your better choice because you have higher data density. But the lower frequencies travel better. So if you want to cover a large range, the lower frequencies are better. So if you have a radio station and you want to broadcast all these talk radio yahoos, nobody really cares about the quality of sound for talk radio as long as you can make it out clearly. And so AM is the best mode for the talk radio because you have a larger range you can cover. But if you're playing classical music, you want to hear the nuanced sound, you want to have more data in there so you can have better reproduction of the sound. And so FM is the better choice for the high quality sound options. So there's different reasons for the dials. And of course, they were developed at different times. It used to be your car always had just an AM radio. You know, I came to America about the right time for them to start to have both in the cars. Moving up, we have microwaves. This is a microwave communicator, right? It receives microwaves from a tower. It emits microwaves that are picked up from that tower. It's kind of scary to think about how much power this has to put out to reach the cell towers that are, half a mile away. And because of that fear, a lot of people are worried that this might cause you damage. It's a microwave. What else do we use that might use as microwaves? A microwave oven. A microwave oven cooks things. I don't want to cook my brain, right? It's a bad thing. And so that's why a lot of people are worried. Now, some things to consider in that discussion. First of all, if you have a really high frequency, you get to an energy that can directly ionize. But you have to be up in ultraviolet. That's why ultraviolet radiation is bad and causes cancer. Because you have a high enough frequency that the energy of the light can break bonds. Break bonds, they reform. If they reform wrong, you have problems. If the energy is below that, if it's in the visible range or lower, and microwaves are definitely lower frequency, you don't have to worry about this. So this isn't just going to break bonds like UV light does. But it does still cook food. Or if you have rabbits that run across the field next to a radar installation, it will cook a rabbit. But to do that, you have to have a high intensity of radiation. It needs to be a wavelength that will be absorbed by water molecules and make them oscillate. And so if this isn't the right frequency of microwaves, and if it's not strong enough microwaves, you don't really have to worry. So this is not going to be likely to cook anything. Despite what you may have seen on YouTube, you can't take our phones, put them like this, and then make them all, call them all, and pop popcorn in the center. Right? That is complete bunk, people just having fun, fooling naive people. So this is a microwave emitter and receiver. It's how we communicate. Those are very useful. If you have a satellite television system, you're using microwaves to communicate with a satellite up there. Now think about that. That's a much larger range communication. And we go walking through that all the time, right? You can't be free of microwaves. I don't know why I'm talking about all of these baloney things. One of our Union College graduates a year ago contacted me and said, can you write to my friend who was another Union College graduate who is spending, I think it was like $3,000 for 4 ashtrays that you put in your house. Well, I swear they look like ashtrays. They're just glass discs that are supposed to protect you from the harmful effects of the microwave radiation from your cell phone while still allowing the cell phone to work. Well, if the radiation is dangerous, how do you stop it from being dangerous? You're going to have to stop that radiation. How's your cell phone still going to work if you stop the radiation? It won't. And yet he's paying thousands of dollars to buy these little ashtrays.
Yes, I did. I wrote a very long treatise, and then when I looked at the webpage, it did say at the very bottom that there is no evidence that these work. Like, seriously, you're paying thousands of dollars when they say there's no evidence that these work. It's, yeah. The fool, the money, you know the premise. Okay, so we go on up from microwaves, we're going up in frequency, we get to infrared. Now, I have to always point this out. When I was a child, I called it infrared. Because I was a child reading, I read the encyclopedia, right? That's what we came to America, Mom and Dad bought the World Book encyclopedias, and me and my siblings all read the encyclopedias. And so I read this as infrared and had no idea what it meant. It was just a type of light. Well, it's not infrared, it's infra, as in below, red. So that's radiation that's below the red part of the visible spectrum. Our bodies are putting off infrared radiation. If we turned off all the lights in the world, you wouldn't see me. Because my radiation is infrared, not visible, our eyes can't see it. But we can get detectors that detect infrared electromagnetic waves. And we can see people, even if it's completely dark. Because we're giving off infrared radiation. Well, you go up higher, you get things hot enough and they start putting off visible light. Right? If you were to make a person, so instead of being around 100 degrees Fahrenheit, they were around 1,000, 2,000 degrees Fahrenheit, you'd start to see them. So visible light goes from red to violet. You probably learned the Roy G. Biv. That's going, red is the lowest frequency, violet is the highest frequency that our eyes can see. And it's a very limited range of frequencies. Notice this is a big number, 10 to the 14th hertz. So 4.3 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz is what it shows here. Or we usually talk about wavelength for light. We talk about the wavelength of light going from 700 nanometers for red down to 400 nanometers for blue. Now, something that's kind of cool is to change this instead of 700, just go out to 750 nanometers. And you're probably saying, why, good sir, should I change that? Well, there's not a strict cutoff point for where you can see and can't see. You just become less and less effective. But if you change that to 750, then this changes to 4.0. And then if you look at the frequency, it's 4 times 10 to the 14th to 7.5 times 10 to the 14th, or 750 nanometers to 400 nanometers. It's the same numbers to memorize for both sides. So that's kind of a convenient way to remember it, so you just have the same numbers. So that's the visible spectrum. You go to higher frequency, you have ultraviolet light. Ultra means above. Violet is the highest frequency that we see. So ultraviolet's above what we see. X-rays and gamma rays are not defined by their frequencies. They're defined by their sources. X-rays are produced from electrons falling to energy states, to orbitals that are close to the nucleus. So let's say you have a copper atom, and you have an electron that falls from n equals 4 to n equals 1. That creates an X-ray. In a hydrogen atom, if an X-ray falls from, or if an electron falls from 4 to 1, we won't consider it an X-ray because the nucleus just doesn't have enough charge to make that much energy. But that's where X-rays come from. Gamma rays come from the nucleus of atoms. So in the nucleus of atoms, I have protons and neutrons. And those protons and neutrons, you can think of them kind of like stacked blocks. And sometimes the blocks aren't stacked efficiently and they can fall down to a lower level. And when they do that, the blocks give off sound. We hear them falling. Well, in the nucleus, when it rearranges to a more stable configuration, it gives off the energy in electromagnetic radiation, in ultraviolet light. So that's, it's ultraviolet light, and we call it gamma rays if it comes from the nucleus. Typically, gamma rays are higher frequencies than X-rays, but you see the overlap here, and the overlap is because it's based on the source, not actually the frequency. This says, okay, this is an expansion of that. I was like, it says the FM radio is in the visible spectrum? No. Okay, I was accurate. Okay, we're almost out of time. What is the wavelength range for visible light? Notice all of them are 400 to 750. It's the units that's different. And those are actually in order of shorter and shorter as you go from top to bottom. Terry. Okay. People are closing in. Nanometers was correct. All right, so this ends our discussion on the electromagnetic waves, and we will start with optics, with light, after this. So have a good